Okay, so it's our great pleasure to have Adrian Ioana today. So Adrian Ioana is a professor at the University of California, San Diego, acclaimed for his groundbreaking work in functional analysis, operator algebra, and ergodic theory, with a particular focus on Neumann algebra and group action. He was an invited speaker at the International Congress of Mathematicians in 2018. And today he will talk about Wreath-like product group and their von Neumann algebra, W star superrigidity and outer automorphism group. Adrian, please start.
Thank you for the introduction, Sebastian, and thank you everyone for coming. So my talk will be about a collection of rigidity results for group von Neumann algebras, and specifically for a class of groups called Wreath-like product groups. And so most of what I'll tell you about is joint work with Ionut Chifan, Denis, Osin, and BIMSA. So let me get started with a little bit of motivation for studying group von Neumann algebras. And start by recalling the basic definition here, which is if you're given a countable group G, and we denote by lambda the left regular representation of G. So this is a homomorphism from G to the unitary group of the Hilbert space L2 of G, where lambda of G is a unitary, which takes the Dirac mass at H to the Dirac mass of G of H. So this is the left regular representation. And then the group von Neumann algebra of G is simply defined as the weak operator closure of the span of the image of the left regular representation. So the span of the lambda G's form a star algebra, and taking the weak operator topology, closure forms a von Neumann algebra. So a weakly closed star algebra. And once you have this this construction, it's a natural question that's been studied now for a long time to try to classify L of G in terms of the group G, and also to determine what the invariants of L of G are, again, depending on the group. And just to make sure we're on the same page, so the two invariants that will appear in this talk for L of G are the outer automorphism group and the fundamental group, which I'll consider for two unfactors M. So out of M is defined as the quotient of the group of automorphisms of M. So these are star isomorphisms of M onto itself, mod out by inner automorphisms. Whereas the fundamental group of M, this was defined by Murray and von Neumann, is the multiplicative group of positive integers, T, such that the T amplification M to the power T is isomorphic to M. So these will be the two main invariants I'll be concerned with. And then the thing I want to tell you is that already this problem of classifying L of G was considered by Murray and von Neumann, who introduced the construction of the group von Neumann algebra. So they proved three facts that I want to recall. First, they showed that L of G is a factor, is a 2-1 factor. So this means that L of G is a simple von Neumann algebra that admits a trace and is infinite dimensional, if and only if the group G is ICC. So this stands for infinite conjugacy class, and means that the conjugacy class of every non-trivial element of G is infinite. So that's a very easy characterization of factoriality. Murray and von Neumann also proved that if G is an ICC group that is locally finite, so this means that G is an increasing union of finite subgroups, then L of G is isomorphic to the unique hyperfinite one factor R. And then they also showed that not all groups give rise to the hyperfinite one factor R by proving that L of F2, the von Neumann algebra of the free group on two generators, is not isomorphic to R. So already back in the 40s, they were able to find two groups with non-isomorphic von Neumann algebras. Now, moving to the 70s, there was a lot of progress on the classification problem done by Kohn, who essentially extended the second item here to all amenable groups. So we just recall that a group G, a countable group, so for me, all groups will be countable, is called amenable if the left regular representation lambda has almost invariant vectors, which means that there's a sequence in the Hilbert space, so Xn in L2 of G, which are all unit vectors, such that Xn are almost lambda invariant, meaning that lambda G Xn minus Xn goes to 0 in norm 2 for every group element G. And this is a broad class of groups. It includes all abelian or solvable groups. And what Kohn proves is that for every amenable group G that's ICC, the Van Neumann algebra, the 2-1 factorial of G, is isomorphic to the hyperfinite 2-1 factor R. In particular, this implies that L of G has the same invariance as R. So the outer automorphism group of L of G is isomorphic to the outer automorphism group of R, which is known to be a huge group. This is a group that contains, for instance, all second countable locally compact groups. And also the fundamental group of L of G is the same as the fundamental group of R and is as large as possible. So it is the whole group, multiplicative group of positive reals. So that's what Kohn proved. And you can look at this by saying that the Neumann algebras and their invariants forget any properties of an amenable group. So regardless what amenable group you take, as long as it's ICC, you always get the same Van Neumann algebra and the same invariance. So there's nothing among the algebraic properties of the group that survive when you pass to the Van Neumann algebra. The rest of my talk for today will be about opposite types of phenomenon. So these are rigidity phenomenon for Van Neumann algebras of non-amenable groups, which will show that sometimes it's possible to even recover the whole group or the group isomorphism class from the Van Neumann algebra. And so my talk will focus on one property in particular, that's property T. So the first rigidity result for Van Neumann algebras was obtained by Alain Kohn in 1980, when he proved that for every ICC property T group G, both the outer automorphism group and the fundamental group of L of G are countable. So as opposed to the case where G is amenable, the outer automorphism group and the fundamental group are small when the group G has property T. And what's property T? So group G is said to have Kazhdan's property T if any unitary representation of G with almost invariant vectors has non-zero invariant vectors. And of course, this is a property that's very much opposite to amenability. And it's a simple exercise to show that if a group has both Kazhdan's property T and is amenable, then it must be finite. So Kazhdan's property T says that the group G doesn't have unitary representations with almost invariant vectors for non-trivial reasons. All almost invariant vectors come from actual invariant vectors. And although this is a very strong property, it is satisfied by many groups. So the classical examples already due to Kazhdan are the higher rank lattices, such as SLNZ with n at least 3. Also, random groups, for instance, random groups in Gromov's density model, where the parameter T in the density model is in the open interval 1/3, 1/2. So these groups are also known to have property T with overwhelming probability and also to be torsion-free and hyperbolic. And a more recent result from about 5 years ago is that the automorphism group of any free group on at least 4 generators also has property T. So this is a result that was first proved by Novak, Kaluba, and Ozawa for k equals 5, and then by Novak, Kaluba, and Kilak for k at least 6, and Nietzsche for k equals 4. Okay, so
can you hear me? Okay. What's the meaning of torsion-free hyperbolic? You mean it should be both Gromov's density model and torsion-free hyperbolic?
So the meaning, yes, that's a good question. So so in two, what I mean is that random groups in Grombow's density model with D between 1/3 and 1/2 have property T and are torsion-free and hyperbolic.
Okay.
Okay, that's not an assumption. That's a property of such random. Is that okay?
Yeah.
Okay, perfect. So now the next thing I want to tell you about is Cohn's rigidity conjecture, which is a conjecture that Cohn made soon after proving his rigidity theorem. So this says that if this predicts that if G and H are ICC property T groups, such that their Van Neumann algebras are isomorphic, then the groups G and H should be isomorphic. So this is very much opposite to what happens for amenable groups. For ICC property T groups, one expects that there is no unexpected isomorphism of group Van Neumann algebras. And let me mention a few results that support this conjecture. So the first is due to Cohn and Jones from 1983, who showed that property T is an invariant of L of G, meaning that if two groups have the same Van Neumann algebra or isomorphic Van Neumann algebras, and one of the groups has property T, then so does the second one. And then another result I want to mention from the 80s is due to Cowling and Hagerup, who were able to show that if you take lattices in SP1N, so these are lattices, so SP1N has property T's, and so does any lattice. So then as you vary N, the lattices will have non-isomorphic Van Neumann algebras. So the lattices are known to be non-isomorphic, and if you want, this confirms Cohn's rigidity conjecture for these groups. So more recently, in the 2000s, Ozawa proved that there exist uncountably many non-isomorphic property T group factors. So there's uncountably many ICC property T groups which have pairwise non-isomorphic Van Neumann algebras. This again is predicted by Cohn's rigidity conjecture because it was known by work of Grigorchuk and Olshansky that or I think it's Gromov and Olshansky, that there were uncountably many non-isomorphic property T groups. And if you believe Cohn's rigidity conjecture, those should have non-isomorphic Van Neumann algebras as well. And the last result in this sequence is due to Popa, who proved that the map sending G to L of G is countable to 1 for ICC property T groups, meaning that you cannot have uncountably many property T groups that give you an isomorphic Van Neumann algebra. So these are all very nice results, but I should say that despite of this, there was really not much progress on Cohn's rigidity conjecture. And this is despite the fact that there's been quite a bit of interest in it over the years. So for instance, in 2000, von Jones conjectured that related to Cohn's rigidity conjecture that if G is an ICC property T group, then the outer automorphism group of L of G should be given by the semi-direct product of the character group of G and the outer automorphism group of G. So what this means really is that L of G only has automorphisms that come from automorphisms of the group and characters of the group. I should also say that Jones' original conjecture missed this character part. This was added later by Popa when he strengthened Cohn's rigidity conjecture, so I'll cover that as well. But the other thing I want to mention is that Cohn's rigidity conjecture is also...
Hello?
Yes?
Yeah,
Yes.
can you really, I did not understood the last line regarding Popa 26.
I will get to that. So all this, I was just making a historical note that the original conjecture of Cohn didn't have this character term and is therefore incorrect as stated. But you need to add
the list. You say countable to 1 for ICC. I don't understand.
What does that mean? Yeah, so it means that it's exactly accountable to 1 up to isomorphism on both sides. So it means that if you look at L of G up to isomorphism, then you can have at most countably many ICC property T groups that give you the same Van Neumann algebra. So in other words, you cannot have uncountably many ICC property T groups that are pairwise non-isomorphic and whose Van Neumann algebras are isomorphic.
Yes. Thank you.
Oh, you're welcome. Another remark I want to make here is that Cohen's rigidity conjecture is equivalent to a formally stronger statement saying that every ICC property T group G is W star superrigid. So a group is W star superrigid if whenever L of G is isomorphic to L of H for any group H, then that group H must be isomorphic to G. So superrigidity here is a very strong property. It says that G is the only group that gives you the Van Neumann algebra L of G. So in a very strong sense, you can kind of recover G from the isomorphism class of L of G. And the reason Cohen's rigidity conjecture is equivalent to this is because if you have an ICC property T group G and L of G is isomorphic to L of H, then by Cohen and Jones's result, H also has property T. So if you have Cohen's rigidity conjecture, then G must be isomorphic to H. And I mentioned this also because in 2006, Popper strengthened Cohen's rigidity conjecture in a way that also subsumes Jones' conjecture. So specifically, Popper conjecture not only that isomorphism of L of G with L of H implies that G is isomorphic to H, but also all such isomorphisms must come in a very specific way. So what he did is the following. So let G be an ICC property T group and H be any group, and consider any isomorphism theta between an amplification of L of G and L of H. Then automatically T must be equal to 1, and there must be a unitary. So up to unitary conjugacy, theta takes lambda of G to a scalar eta of G. So this is just a complex number modulo 1 times lambda of delta of G, where delta is an isomorphism between the groups G and H. So in other words, Popper conjectures that any isomorphism between an amplification L of G and L of H must impose that T is 1, and it must come from an isomorphism of the groups and a character of the first group. And in particular, this implies, this would subsume the conjecture about the outer automorphism group of L of G if you take G equals to H. All right, so my goal is to tell you about this work with Bin and Denis and Ionut, in which we gave examples of groups that satisfy all of these conjectures. But before I do so, I'm going to take a little bit detour and motivate that with some results from deformation rigidity theory. So that's a theory that Popper initiated in about 20 years ago, and it's led to a lot of progress in the classification of group Van Neumann algebras. Here, I'm just going to mention two results that are very relevant to what I'll tell you about later. And for that, let me recall the construction of Wreath products of groups. So if A and B are two groups, then the Wreath product, the regular Wreath product of A and B, is a semi-direct product formed as follows. So it's A Wreath B. You take the direct sum of A indexed by the group B, and on this group, B acts by shifting the copies of A. The resulting semi-direct product is the regular Wreath product of A and B. More generally, you can define the generalized Wreath product associated to A and an action of B on a set I, where again, you replace the direct sum of A's indexed by B with the direct sum of A's indexed by the set I on which B acts. These are the regular and generalized Wreath products. And Popper proved in 2004 that if B1 and B2 are ICC property T groups, and the Wreath product of Z with B1 and of Z with B2 have isomorphic Van Neumann algebras, then B1 is necessarily isomorphic to B2. So this can be viewed as somewhat of a relative version of Cohn's rigidity conjecture. So, if you pass from ICC groups to the Wreath product with Z, then you can recover them from the von Neumann algebras. And then a few years later, together with Popa and Vass, we gave the first examples of W star superrigid groups. And specifically, we showed that certain generalized Wreath product groups of the group Zima to Z with with a group B with the generalized Wreath product of Zima to Z with some action B on I of some group B and a set I. These are W star superrigid. I'm not going to be more specific than that because the construction is a bit more complicated. It's not so relevant. But the point is that there are generalized Wreath products that are W star superrigid. What I do want to emphasize is that first, the reason we couldn't prove with Stefan and Sorin that Wreath products are W star superrigid is because this is never the case, essentially. Wreath product with abelian base, at least, are never W star superrigid. And you can see this as follows. So if you take any two abelian groups A1 and A2, which have the same cardinality, for instance, you can take A1 and A2 to be both infinite. So take A1 to be Z and A2 to be Z squared. Then the Wreath product of A1 with B and A2 with B have isomorphic von Neumann algebras. So in particular, these are non-isomorphic groups that have isomorphic von Neumann algebra, so neither of them can be W star superrigid. So that's why we need to pass to Wreath-like products. But again, so my motivation here was to look for examples for Cohn's rigidity conjecture, and neither Wreath product groups nor generalized Wreath products have property T. So this is the second remark here, that non-trivial generalized Wreath products do not have property T. And specifically, if you take any non-trivial group A and a set I which is infinite, then the generalized Wreath product of A with B over I does not have property T. Okay, so generalized Wreath product only has property T in kind of trivial situations where the set is finite or the group A is trivial. So the rest of my talk, or the next part of my talk at least, will be about certain groups that are relatives of Wreath products. So we call them Wreath-like products, which unlike Wreath products are W star superrigid and have property T. But these will be groups that have a certain algebra. Sorry?
Can I ask you about the first result of Popa and the first remark you say with product with abelian bases are not W star superrigid, but the first result of Popa, it looks like Z is an abelian group, and what the result looks like it's a W star superrigid.
Yeah, so W star superrigidity would mean for a group G is that L of G is isomorphic to L of H for any H, then G is isomorphic to H.
Yeah, okay.
So here H is of a specific kind. So this is a W star rigidity result showing that within a certain class of groups, isomorphic von Neumann algebras imply isomorphism of groups, but it doesn't allow for arbitrary groups.
I see. Thank you.
Oh, you are welcome. So let's see, are there any other questions before I move on?
No, it's okay.
Okay, perfect then. So, all right, so in order to introduce these Wreath-like products, I'm going to start with a remark, sort of giving you a way of looking at just Wreath products in a different way. So let me take with G to be the free product of two groups A and B. Then, if you look at the normal closure of A in G, so this is the smallest normal subgroup of G which contains A, then you can see right away that the normal closure is simply a free product of conjugates of A, where the conjugates are done with elements of B. So it's a free product of B, A, B inverse with B ranging in the second free product group B. And then you also notice that G is generated by the normal closure of A and B. So let me consider the following subgroup S of G. So this is the subgroup generated by the commutators of all pairs, so different conjugates of A in this free product. So this is the commutator of BA, B inverse with CA, C inverse over all B and C in B, but different. Then S is a normal subgroup of the normal closure of A. And of course, when you quotient the normal closure of A by S, what you've done is to quotient out by the commutators of all of these copies of A. So from the free product, you're going to obtain the direct sum of A indexed by the group B. But what's interesting is that, moreover, the group S is also normal in G. And it's not hard to see that when you take the quotient of G over S, you get the Wreath product of A and B. So it's the semi-direct product of the direct sum of A's copies of A indexed by B, semi-direct product with B. Okay, so what this says is that you can obtain the Wreath product in a very easy way by taking certain quotients. So this is the method that we want to generalize. And first, let me give you the following definition. So a subgroup A in G is called a Cohen-Linden subgroup if the normal closure of A can be written as a, so this is a typo, it should be as a free product of conjugates of A. So it should be TA T inverse, where T, the set T, is a transversal for the normal subgroup, for the normal closure of A in G. Okay, so a Cohen-Linden subgroup is one that for which the normal closure has such a free product decomposition of different conjugates of A. Okay, so what are some examples? So as we already saw, any group A is a Cohen-Linden subgroup of the free product with A with any other group B. But what Cohen and Linden discovered in 1963, which is what gave the name to this property, is that also maximal cyclic subgroups A of any free group Fn have the Cohen-Linden property, are Cohen-Linden subgroups. What we'll see next is that, in fact, Cohen-Linden subgroups exist in abundance in hyperbolic groups. But before I do that, let me tell you what the use of this property is. So here's the proposition. So assume that A in G is a Cohen-Linden subgroup. Then we're going to do exactly the same procedure as we did for Wreath products. So take S to be the group generated by the commutator of all the conjugates of A, BA, B inverse, CA, C inverse, where these are different conjugates in the free product decomposition of the normal closure of A. Then in the same way we notice in the remark, you can see that S is not only a normal subgroup of the normal closure of A, but it's also a normal subgroup of G. And it turns out that when you do the quotient G mod S, this is a Wreath-like product of A and G mod the normal closure of A. So what is this Wreath-like product? So here's the definition. So a group G is a Wreath-like product of two groups A and B. In symbols, G belongs to the class WR A and B. If there's a short exact sequence with the group G in the middle, the quotient group is B, and the kernel, the normal subgroup, is the direct sum of A indexed by the group B in such a way that when you take an element of G and you conjugate one of the copies of A, so let's say you conjugate the B copy of A, then this is a different copy of A, well, given specifically by epsilon G times B. So a Wreath-like product of A and B is a group that sits in such a short exact sequence in such a way that it has the direct sum of A's indexed by B as a normal subgroup, and the conjugation action permutes the copies of A. So what is this different from the Wreath product? You can see right away that the Wreath product of A and B sits in such a short exact sequence. And in fact, the group G will be the Reeve product of A and B exactly when the short exact sequence is split. So the point of our work is that there are many non-split such exact sequences that will give us interesting and new examples of Reeve-like product groups. So, so I'm not going to go in a lot of details here, but let me recall a theorem from geometric group theory due to Dachmani, Girardel, and Osin, and also with input from Binson. So this is what the theorem says. So in essence, what the theorem says is that in hyperbolic groups or relatively hyperbolic groups, you have lots of Cohen-Linden type subgroups. So this is a bit technical, but I'll mention it quickly. So if a group G is hyperbolic relative to a subgroup H, then for every normal subgroup N of H, which is sufficiently deep, what this means is that N avoids a finite set of non-trivial elements of H. So it avoids this sort of bad subset of H. Then we have that the normal closure of N in G is a free product of conjugates of N over conjugates lying in a certain left transversal. And moreover, when you do the quotient of G over the normal closure of N, this will maintain relative hyperbolicity relative to H mod N. Okay, so this is saying that this type of quotienting techniques maintains relative hyperbolicity plus this normal closure has a free product structure. So, so this implies, with a bit of work, that ICC hyperbolic groups have a lot of Wreath-like quotients. So this is one of the theorems that we proved a few years ago. So take G to be any ICC hyperbolic group. So this is any, for instance, if you take G to be a torsion-free hyperbolic group, then for every finally generated group A, there exists a quotient K of G such that that quotient is the Wreath-like product of A, the arbitrary finally generated group A, and some ICC hyperbolic B. Okay, so this means that there's lots of Wreath-like products that are Wreath-like products of some arbitrary finally generated group with some hyperbolic group B. And moreover, these groups can be obtained as the quotient of any ICC hyperbolic group. And it's crucial here that we can take G to be any hyperbolic group because there are hyperbolic groups with property T. And in case G has property T, then so does K. So there's lots of Wreath-like product groups that have property T. Okay, and in particular, this tells you there's lots of Wreath-like product groups that are not Wreath products because, as I noticed earlier, Wreath products never have property T. So let me mention a quick application of this. This is in a different paper with Chifan, Daniel Drimbe. So using this statement, the theorem A, when G is ICC hyperbolic with property T, when A, the finally generated group A, is a free group on two generators, this alone allowed us to prove that every separable 2-1 factor embeds into a 2-1 factor with property T. Okay, so this is the Neumann algebraic analog of a result of Olshansky and Delzan from the 90s, showing that every countable group embeds into a countable group with property T. All right, so so before I move on to the next page, the sort of takeaway from this page is that there are lots of Wreath-like products with property T, and in fact, there are lots of Wreath-like products with property T that have A, B arbitrary finally generated and B ICC hyperbolic. Okay, so the next thing to tell you about is that a lot of these groups are W star superrigid. And before that, I should say that after the work with Popa and Vass from 2010, there were several other works that provided W star superrigid groups, but all of these works gave examples that did not have property T, and the reason is that all the groups that were considered are either generalized Wreath products of variations of such, or amalgamated free products, none of which have property T. So with Chifan, Osin, and some, in the same paper, we proved that if G is a Wreath-like product of A and B and has property T, where A is non-trivial abelian and B is ICC hyperbolic, then G is W star superrigid. Okay, so in combination with theorem A, this gives you lots of examples of W star superrigid groups with property T, because as we saw, any ICC hyperbolic group with property T will have such a quotient G. So I should mention this. So these are the first examples of W star superrigid groups with property T. So these are and in fact, we showed that there are continuum many such groups. So there exists a continuum of property T groups, all of which are ICC, such that each group in that family is W star superrigid. And if you want some more specific examples where thing to note is that our theorem B not only applies to regular Wreath-like products, but it applies to generalized Wreath-like products as well. So the definition of generalized Wreath-like products is analogous. You just have to change the action of B on itself to the action of B on some arbitrary set I. So theorem B also applies to such generalized Wreath-like products, provided that the action of B on I has amenable stabilizers. And by applying this more general theorem, we prove the following corollary. So start with K to be any torsion-free property T group. And you remember here I can take K to be one of these random groups of Gromov, and take G to be any non-trivial element of K. So then K admits the following W star superrigid groups. So take the quotient of K by the commutator subgroup of the normal closure of G to the n. So you take the normal closure of G to the n in K. This is some normal subgroup. You take the commutator subgroup of the normal closure. That is again a normal subgroup of K. The quotient of K over this normal subgroup is ICC W star superrigid and has property T for every n that's large enough. Okay, so starting with a torsion-free hyperbolic group, you get W star superrigid groups with property T for any of its elements. This is if you want, a concrete family of W star superrigid groups with property T. And before I move on to tell you a bit more about some other results in this direction, let me mention a recent result related to our theorem. So theorem B shows that if G is an theorem B, then L of H is isomorphic to L of G if and only if H is isomorphic to G for any H. And there's a recent result of Chifan with Adriana Fernandez Cuero and Hui Tan from last year, who proved that sort of an improved version of this result, where so what the result shows is that if you now replace G by G times Z, so the direct sub with the group Z, this is no longer an ICC group, it's a group with center. And so the question is to what extent can you recover G from the von Neumann algebra of this non-ICC group? So what they showed is that L of H is isomorphic to L of G direct sum with Z if and only if H itself is the direct sum of G with an infinite abelian group Z. All right, so let's see. Are there any other questions? Another good moment to stop.
It's okay. It's okay.
All right, so let me recall again what theorem B said. So if G is a Wreath-like product of A and B, which has property T with A non-trivial abelian and B ICC hyperbolic, then the group G is W star superrigid. In particular, when you know that the group is W star superrigid, so in fact, our theorem showing W star superrigid is much more precise. It establishes Poppa's conjecture for these groups G. So in particular, it implies that the outer automorphism group of L of G is isomorphic to the character group of G with the outer automorphism group of G, and that the fundamental group of L of G is trivial. So there's two comments that I want to make related to this. So the first one is that this result provides additional examples of property T groups such that the fundamental group of L of G is trivial. The first examples were found just a few years ago by Chifan, Das, Huday, and Khan. So our theorem provides examples of a different kind. And second, the remark I want to make is that theorem B, showing that the outer automorphism group of LOG is what one expects, settles Jones's out conjecture for all such groups G. So these are the first examples of groups, property T groups for which Jones's conjecture holds. However, there's a caveat here that for the groups G that we considered in theorem B, although we could show that the outer automorphism group of L of G is isomorphic to, all the automorphisms of L of G come from characters and outer automorphisms of G, we could not compute the outer automorphism group of the group or the character group. So this means that we couldn't actually compute explicitly the outer automorphism group of L of G. But and moreover, to make things worse, for the groups that we considered, this outer automorphism group of L of G is always finite. And this comes from the fact that B is hyperbolic. So this had these advantages that we couldn't get explicit computations. And moreover, the outer automorphism group of L of G was always finite. But we still couldn't decide which finite group it is. Okay, so we addressed this problem in a second paper. And we did so by first establishing a theorem, which has if you want, a sort of weaker conclusion, but much stronger, but which covers a much larger class of examples of groups. So I'm no longer interested in W star superrigidity. I'm just going to take now two groups G and H, which are generalized Wreath-like products of A with an action B on I. So these are property T groups. And I'm assuming, as before, that A is non-trivial and abelian, and B satisfies the following somewhat long condition. So I'll say it, but so just to unpack it. So B is an ICC non-parabolic subgroup of a relatively hyperbolic group, which has finally generated residually finite parabolics, and the action of B on I is a faithful action with infinite orbits. So I should say that, in essence, what this is saying is that B is no longer required to be hyperbolic. It's okay to be relatively hyperbolic. And moreover, the action of B on I is not required to have amenable stabilizers, which having amenable stabilizer is almost as being the regular action of B on B. But so we only require that the action is faithful and has infinite orbits. So under these very general conditions, we can prove that any isomorphism between an amplification of L of G and L of H must come in the way conjectured by Poppa. So if you have an isomorphism between L of G to the power T and L of H, then this T forces T to be 1, and the isomorphism comes from a group isomorphism and a character of the first groups. So in particular, if I only look at G equals H, I get that the group G satisfies Jones' conjecture. So the outer automorphism group of L of G is isomorphic to the character group of G semi-direct product with the outer automorphism group of G. And moreover, the fundamental group of L of G is trivial. Okay, so theorem D shows that if you have, in particular, shows that if you have a generalized Wreath-like product group with property T, where A is non-trivial abelian and B satisfies these more general conditions, then you still get all the consequences you want for the outer automorphism group and the fundamental group of L of G. And this is useful because in addition to this result, we could provide such generalized Wreath-like products that had prescribed outer automorphism groups and character groups. So that's the next thing I want to tell you about. But before I go there, let me mention a result of Minassian from 2009, who showed that for every countable group Q, there exists an ICC property T group G, such that the outer automorphism group of G is that countable group Q, and the character group of G is trivial. Okay, so if you have a property T group G, then the outer automorphism group of G is countable. Minassian proved that any countable group arises as the outer automorphism group of a property T group. However, this doesn't combine with our theorem because Minassian's groups have two conjugacy classes. In particular, they're simple, so they are definitely not Wreath-like products. So instead, we prove the following result. So for every countable group Q and every countable abelian group A, there exists an ICC property T group G with the following properties. The outer automorphism group of G is isomorphic to Q. So it's any figured one. The character group of G is 1. And G is a Wreath-like product of your countable abelian group A with an action B on I that satisfies the condition star in the previous theorem. Okay, so remember these conditions on G are enough to guarantee that Jones conjecture holds for G. And before I state a consequence of this theorem, which will be my last slide, let me just say a few words about how we prove this theorem E. So this relies on a couple of ingredients. The first one is a consequence of work of Wise, Haglund, Wise, and Agel. And it's a fact showing that every countable group Q can be embedded into a quotient of two groups S mod R, where S and R are finally generated. Moreover, S is residually finite and torsion-free. So our theorem proceeds by taking the group Q and embedding it in such a quotient. So that's the first ingredient. The second ingredient is a calculation of outer automorphism groups for certain Wreath-like products. So this is a bit technical, and so I won't spend much time on it. But here's how it goes roughly. So you start with a group H, which is a Wreath-like product of A with an action of K on I. And here the set I is a coset space K mod R, where R is a null-normal subgroup of K. So this means that any different conjugates of R in K intersect trivially. And now, because H is a Wreath-like product of A and K acting on I, there's a quotient homomorphism from H to K. So let me denote that by epsilon. And let me also consider a subgroup B that's between R and K, and moreover, is normal in K. If I take the preimage of that subgroup B through the homomorphism G, so this will be a normal subgroup of H. And in fact, you can show that it's a Wreath-like product of A with the action of B on I. And moreover, what you can show is that because G is normal in H, of course, any conjugation with an element of H gives an automorphism of G. And in fact, with a little bit of work, you can show that the quotient group H mod G embeds in the outer automorphism group of G. And finally, what we show here is that under certain conditions, this embedding of H mod G into the outer automorphism of G is in fact an isomorphism. So I won't say more about that, but those are the two main ingredients: a calculation of automorphisms and this fact, this geometric group theoretic fact that I mentioned above. Okay, so once again, what theorem AE says is that there are Wreath-like products that satisfy our previous result, theorem D, and moreover have prescribed outer automorphism groups and trivial character groups. So if we combine theorems D and E, they together imply the following result. So for every countable group Q, there exists, in fact, there exists one ICC property group G, and in fact, continue many such ICC property groups, such that the outer automorphism group of L of G is Q, is isomorphic to Q, and the fundamental group of L of G is trivial. So, so this means that the outer automorphism group of the Neumann algebra property T group can be any countable group. And remember that Cohn proved in 1980 that out of L of G is always countable when G has property T and is ICC. And here we proved that it can be any countable group. So I should say that theorem F provides, in fact, the first explicit calculations of outer automorphism groups of L of G for ICC property T groups G. And in fact, it settles the problem of determining which groups arises out of L of G for ICC property T groups G by showing that it's exactly, so these groups are exactly all the countable groups. So this is the last result I want to tell you about. And I will just end with some open problems. So the first open problem is to try to address the analogous question for the fundamental group of L of G. So which countable subgroups of positive reals arise at the fundamental group of L of G for ICC property T groups G? Here, as I mentioned earlier, Popa conjectured in 2006 as part of his strengthening of Cohn's rigidity conjecture that this fundamental group should always be trivial. And I should say that now there are a few calculations of fundamental groups for property T groups G, and they're all trivial. And so this is wide open whether, in general, the fundamental group of L of G has to be trivial. And then I also want to mention sort of some classical problems going back to Cohn's conjecture in 1980 and his original motivation, which is to settle some of these problems for the sort of classical property T groups, which are the higher rank lattices. So this is the second problem, is to try to prove that SLNZ, or rather PSLNZ, so that you get an ICC group. So the PSLNZ give the arithmetic lattices PSLNZ give non-isomorphic to 1 factors as you vary n greater or equal than 3, and also to calculate the outer automorphism group and the fundamental group of the Van Neumann algebra of SLNZ for n at least 3. So these two problems are wide open currently. And anyways, there's a lot to do. So I will stop here, and thank you so much for listening.
Very much. So question. I have several questions.
Okay.
So so you started by mentioning the case of the minimal group, and then the property T group, which has a kind of perpendicular phenomenon. One is completely non-rigid, and the other is completely expected to be completely rigid.
Mm-hmm.
So in the world of quant factor, what do you have in between? In between something amenable or something property T? There are some.
there's a lot in between, and there's a lot that I didn't cover. So for instance, if you there's of course the free group factors. These are non-amenable, don't have property T, and the free group factor problem is the free group isomorphism problem is wide open. There's also groups that have both a little bit of free groups and a little bit of property T, like this semi-direct product, say Z squared crosses L2Z, um, where Popa showed that the fundamental group is trivial. But in general, like, I mean, there's a wide variety of groups. Property T is like a large class of non-amenable groups, is somehow, in a way, the most non-amenable groups that you can get. So they're at the exact opposite. And even for them, there's a lot that we don't know, even though they're very strongly non-amenable. So that's why I focus on that class. But there is a lot of literature from the last, say, 20 years that focuses on various classes of non-amenable groups that address what you're wondering about.
So, the other question is, so your result address in some sense the conjecture of cone in some specific, in this class of example. So it's do you believe it's true in general, or that's
That's a good question. I don't have a strong feeling because, again, the class of property T groups is really huge. Like random groups are property T. There's all this, all the lattice, high rank lattices. There's just so it's hard to know if this should be true in general. However, I should say there's no counterexample to any of these conjectures. So if I go back to the conjectures, so the motivating conjecture that I heard early on. So for these conjectures, they're all open as stated. So it's not like we know an example to say any two property T groups that give you isomorphic Neumann algebra, but the groups are non-isomorphic. So these are all wide open.
Do you think they can have some logical non-decidable phenomena here? It can be non-decidable, like
Undecidable? That I don't know.
because when you have infinite group, you can have sometimes this kind of phenomenon.
I mean, I wouldn't be surprised if there are some property groups that are very strange, that maybe they can have some unexpected isomorphism. But so far, nobody has been able to construct such examples. So if they are, they must be very exotic.
I have a last question.
Question. For your last for your own questions, the last one, do you have any idea to guess what is the fundamental group? I'm guessing.
Well, it's the same kind of question. I mean, I don't see a reason why you shouldn't have countable subgroups other than the trivial one. I don't see a sort of a fundamental reason why you shouldn't.
Okay.
So, yeah.
Also, another question is about you are talking about you don't know the structure of about the final group. I think you automorphism of LG, some kind of LG. Can you define whether there's a normal subgroup or something like that, or what is the difficulty inside?
What is difficult for what? Sorry, I didn't quite understand the question.
I mean, the final group structure.
The finite, that I mentioned earlier. So there is basically, so is this result that I mentioned here, when you, in theorem B, there's just, we don't have a way of computing explicitly the outer automorphism group or the character group of G. It's just not, our construction is not fine enough to determine those. And in fact, I mean, it's possible so okay, the best you could hope in this theorem B is to show that out of L of G can be any finite group, because as I mentioned, because B is ICC and hyperbolic, there's a result of Paulin and Besvina showing that hyperbolic groups with property T have finite outer automorphism groups. Character groups of property T groups are also always finite. So if you combine those two, the semi-direct product on the right side is always finite. And I would expect that for pure groups as in theorem B, the right side can be any finite, but we don't have a way of showing that.
Yeah, very nice comment. Thank you very much.
Are you welcome?
I have a last question. The one other. So my question is, you have this conjecture about rigidity phenomenon, but are there conjecture about non-rigidity phenomenon? In fact, I have a very specific question. I will read it. So is there a pair of non-isomorphic torsion-free hyperbolic group that have isomorphic von Neumann algebra?
Torsion-free hyperbolic. I would have to think about that. Nothing comes to mind immediately, but of course, as you might know, it's even an open. This might not be in the direction you're asking, but things like even for the free groups, I think it's
But
for the compact lattice, SL2R, these are
an example for which it is known. This is.
I am not sure that there are such examples. I would have to think about that. Torsion, because you want torsion-free hyperbolic.
Yeah.
Yeah. So the issue there is that if you're, if you're safe, the free group, of course, we have the free group isomorphism problem, and then if you have property T, there's also sorry. So no, actually, yes. So the answer is yes, because by Cowling-Hug group, if we go back, okay, so so Cowling-Hug group proved that if you take two lattices in SP1N and SP1M, these, for if N different than M, these will have non-isomorphic von Neumann algebras. And of course, you can take co-compact lattices. This will be hyperbolic. And there's always, whenever you have, forget in what generality, but you can always pass to a finite index subgroup to avoid torsion. So you definitely in SP1N and SP1M, you'll have torsion-free hyperbolic lattices that will give you non-isomorphic von Neumann algebras, even with property T.
I'm asking about isomorphic von Neumann algebra.
Sorry?
The question is about isomorphic von Neumann algebra, not.
You wanted isomorphic. I'm sorry. If you want isomorphic, well, yes, that's a good question. And I don't know the answer. I don't think, nothing rings a bell. And the reason is, usually there's a few recipes of constructing isomorphic things. They come either from, say, free probability. There's ways of dealing with free products that might be able to give you isomorphic group von Neumann algebras, then Cohn's theorem. So yes, there's not, I cannot think of two examples like that, specifically for hyperbolic, because all the examples are sort of, built around amenable groups or free product groups or things like that. But there might be example. I just cannot think of one now.
Okay, thank you, thank you. So any other question? So if not, we can thank the speaker.
Thank you.
Very nice talk. Thank you.
Oh, thank you very much for the invitation. Yeah.